Thanks, Celine. Okay, so yeah, I'm going to talk about various things which relate to making decisions and also relate to our discussion last night and over the last couple of days. So I just want to immediately acknowledge three people: Richard Arnold from University of Victoria in Wellington, a statistician; Xubin Zhao, who's a PhD student in my group. Xinjiang was a PhD and a postdoc. He's now got a job in Beijing in China, and a lot of this work is from them. So what we would typically like to do in many practical problems is to answer questions that have very low dimensional answers. So we seek answers to questions such as, what is the volume of a particular subsurface reservoir? Well, that's just a scalar. It's a one-dimensional answer, x kilometers cubed. Has more than 1 kiloton of CO2 escaped from the subsurface storage reservoir? That's a yes or no binary answer. It's got no dimension. Which dynamic model explains the true seismicity? We've got a choice of models, 1, 2, 3. It's a discrete answer out of a set. So very low dimensional or even zero dimensional answers that we want. But often they lie within very high dimensional spaces. So, for example, subsurface images. In a subsurface image, every single pixel has the freedom, a continuous freedom over values, and so is an independent dimension. So this image here has about 10,000 dimensions. So we seek a 1 or 0 dimensional answer within a 10,000 dimensional space. And so what I'm going to do today is just talk around some theoretical framework, which we call interrogation theory, but essentially it's a theoretical framework to try to relate these questions to the model spaces we have to use. I'll use a 2D seismic imaging example. It'll be, in fact, this one, to work through an example and show you how some of it works. And now we're at the point where we have been able to do this for a 3D example, and we're now working on 4D examples, so time-dependent examples. And finally, then, I'm going to talk about something quite different, where we move into a domain of what's called radical uncertainty, and I'll come to that later. So we're quite used to dealing with problems like this, where M is the model of interest. Typically, it describes an Earth structure or some process that's going on, or some parameters of a process. The data is something we can record, and F, there's just got to be a relationship between the two, which is the function. But immediately, I'm just going to change this because in mathematical literature, that's not what the terms are called. This is the model, because mathematicians are interested in relationships, not in parameter sets and specific values. These are just called the parameters. And again, the data is the data. So I'm going to use this formulation because when we're interested in, what we're going to be interested in doing is designing experiments and designing methods and processes in order to be able to answer questions which are a function of this whole thing. So we're going to be interested in these relationships. So I'm going to use parameters for M. If I ever say model, I hope I'll be consistent and it will be the relationship, but we'll see. So I'll use this system. So many of us are familiar with the idea of inverse theory. So we have some parameters and their values, and these are related through a forward problem to the data space that we can measure. And the inverse problem, we have to apply inverse theory to go in the opposite direction because we often don't have a direct function that we can pass the data into to get to our parameters. And so typically what is done is that we collect some data and then we try to find the parameter values that best fit the data through our model, through our forward function, if you like. The problem is that if that's what we do, we find the best fit parameters, there's only one thing that we know about those final values. Well, we know the values themselves, but in addition, there's one extra thing we know, and that they are definitely wrong. So if it is a continuous problem, then mathematically it is impossible to find the right answer. So then the only question left is, how wrong are they? How close might they be? How far might they be from the right answer? So that's problematic in the real world where you want to make decisions. If you use best fit answers, they will be wrong. So That brings us into more a probabilistic framework where we, instead of looking for a single best fit answer, we want to find at least a representation of the family of answers that might be true, given the data. And typically nowadays we use something like Bayes' theorem, which is just this formula, which many of you will be familiar with. And the nice thing about Bayes' theorem is it tells us how to get this quantity on the left, which is called the posterior probability distribution function. So something that describes the probability of different models. And in particular, Bayes' theorem tells us the probability of a particular model, particular set of parameter values, I'm already doing it, given some particular observed data set, d-obs here. And so that's what we want. Given that we've measured a particular data set, what is the probability of a given model? And Bayes' rule simply says that this is in terms of this is given in 3 terms. The likelihood, which is, well, if the model was true, what's the probability that we would have observed that data set? So that's really the comparison of the model, I'm doing it again, the parameter values with the data, anyway, whatever. You know what I'm talking about because I'll be pointing. The parameter values with the data. So that's where we compare with the data. This term here is called the prior distribution or probability distribution, which tells us what we knew, essentially says what is the probability of the parameter values given what we knew before. So prior means before we measured the data. And it's not just independently of the data, it should be before so that we don't bias ourselves with the data set. And then finally, this term on the bottom is the evidence, which is essentially a normalization factor for a lot of what we do because it doesn't depend on the parameter values themselves. So that's Bayes' rule, and it seems to give us what we want. The probability that M is true given the model, which relates the parameters to the data, given the observed data, and given our prior information. And that's fine, but the parameter values may describe an image, something like this. And actually, we might be interested in just a part of the image. Let's say this little anomaly here, which might be our reservoir of interest for our CO2 store. And actually, we only want to answer that 1D question, or actually this is a binary question. Has more than a kiloton of CO2 escaped from that store? So the way that Bayes' rule might be applied in this, in this sort of scenario is we might use the information from our image to try to work out how much of the porosity above the reservoir has been accessed by leaking CO2. And if we think about our prior knowledge, well, the more CO2 that's leaked, the more porosity, the more of the space that's been accessed by leaking CO2, we might expect the more CO2 goes up, the more the saturation increases. So the more, essentially, we increase the concentration of CO2 relative to water in that overburden. And so there would be a prior relationship that went like this, the porosity accessed versus the saturation of CO2, they would increase together. We then get some new data like this image, and we find that actually the data is really only sensitive to the bulk volume of CO2 that's changed. And so that means we can have more porosity accessed, but then the saturation must have gone down, or vice versa. It may actually all be concentrated with a high saturation in a small volume. And so the data tells us this. And so the combination in Bayes' rule is what gives us much tighter constraints. We basically, Bayes' rule says multiply this point by point with this to get the answer. So if you just look at, say, the circle here, we see that it's got a high prior probability. It's got a high probability from the data, so it ends up with a high probability here. The cross has a high prior probability, but the data says no. It excludes that possibility, and so it's got a low probability. And here we see one of the issues with using Bayes' rule. In general, we can only plot these pictures because this is a 2-dimensional space, but we're going to work in a 10,000 dimensional space, so we can't plot the pictures. All we have are points where we evaluate these terms. So which points are we going to use? Because we can never look at them in any sense at all. Which points are we going to choose? in particular, which points are we going to choose for this particular question? Because if I ask a very different question, like, what's the structure over here? Clearly, I might want to choose different points. So everything in the whole system now must depend on our question. So what Richard Arnold and I did a few years back was simply just to rephrase a lot of existing theories into a way that's focused around simply questions and answers. So particular questions we might ask and the space of possible answers to those. And if we start at this point, then we can define our forward functions, our parameters, and various even algorithms that we're going to use such that they can all answer these questions to give something in the answer space. That actually is a constraint on all of this lot. We've then got a set of forward functions which allows us to bring in design theory. We had a presentation from Dominic about experimental design. So we're going to design our our experimental system so that we acquire data that maximally informs the answers to these questions. We then perform the experiment or elicitation, whatever it is that we do to collect some data, and we can apply normal, regular inverse theory here to constrain the parameters. But we still haven't answered the questions. In order to answer the questions, we have to take information from all of these different stages and solve a decision problem. So this is going to require decision theory in order to choose an answer from the question. And this answer might be a decision, for example. And then we will accumulate knowledge from this process, and we might go around and iterate to answer the next question and so on. So if we focus on the questions and answers, then we're going to do slightly different things than simply just than we would normally do in the inverse theory schema. So here's a decision. Now let's just go through an example. And I really just want to go through this in a bit of detail to show you that when you want to make a decision, it changes quite substantially what you have to focus on in terms of actually what your theory has to give you and what you have to spend time thinking about. So here's a decision. If a particular reservoir volume is greater than some value V, then it is large enough that we'll consider it to be a CO2 storage asset. So this is the kind of decision which is facing a lot of companies just now, governments just now, and regulators. Because the question is, if we have offshore reservoirs or onshore reservoirs that some of them might just be aquifers, some of them might have been used for hydrocarbons, production or whatever it is. Can we now or can we not consider those to be CO2 assets that we could use for CO2 storage? Now, there are various factors. Let's just consider one of those. Clearly, the volume is going to be a factor there in that decision. So this is what we want to decide. And the sub-question then is, what is the volume of this particular reservoir? And we'll focus on the one that I just introduced for this example. Okay, so first of all, let's parameterize the inverse problem part of this. So we've got a seismic velocity structure, V of x. We're going to acquire some data, which in this case will be full seismic waveforms acquired from the surface. And then we need a forward model, which in this case will be full finite difference modeling of those seismic waveforms given the data. Given the subsurface model or the parameter values shown here. Now, in order to be able to answer a question, we have to then define something called a target function, which takes any particular set of parameter values. So, for example, this image here. It takes the question that we're interested in and transforms those into a space or into a parameter theta where it is possible to answer the question. It doesn't have to be directly an answer, but it's something from which we can start to answer the question given a particular set of parameter values. So in this case, it will transform the velocity structure into the corresponding reservoir volume. Very simple in this case. So it's just going to be a transform. We'll come back to that later because that turns out to be difficult. Then we still haven't answered the question. For that, we have to define what's called a utility function. And this describes the net benefits of any answer, any particular answer we choose, A, given that the true model is T. So this sounds like a bit of a trick because we don't know the true model. But we can do this because, remember, we're going to have, in the end, not just one image here. We're going to have to consider lots and lots of different images because we have uncertainty now in the answer. And so if we consider that as the true structure, what is the net benefit of any particular answer? Because we're not going to give an answer per model. We need one answer for the whole lot. So we need something that defines how, if you like, it's sort of a loss function, but actually it's a benefit function. And notice that one of the key factors here is the squared. That is simply a choice. This is a very simple function, but this squared here is going to define what is the nature of my answer given the true model. And I can have very different structures here. But what is important is that whatever the form of this is, we are going to end up, by playing some mathematical tricks, we end up with different formulae that give us the right way to calculate the answer. And I'll just tell you that under this particular utility function, the answer is this. This, and I'll go through this in a minute, but this is the optimal answer that you can choose given some data and a range of models. And you see it's got two terms in it. This last one is just the Bayesian posterior probability distribution. It's what Bayes' rule gives you. The red one here is the target function, which transforms a model into the space theta where we can answer the question. And then we have to average over all possible models and data. So it's sort of what you would expect under this squared utility function. You get this, what you might expect. We will transform it into something where we can answer the question, and we'll answer the question in that space and average the answers over all the different models. So that's an intuitive one. But if I change this to, instead of having a squared utility, if I just had a modulus, so a one norm utility, we would get a different answer for this. The formula wouldn't be the same. So the utility is key to defining what the quality of the answer is that we're after. Okay, let's have a look in this case. So here's the real truth in our synthetic problem. So there's our little reservoir there. We're going to have just 10 shots, a line of receivers. Here is our prior information about the velocity structure. So we know what it is in the water layer. The receivers, you'll notice, are on the seabed in this simulation. And then the velocities will lie somewhere within this range at each depth. And we're simulating data, real data, with a 4 Hertz wavelength, so nice low frequency data. And we want to evaluate this. So in order to evaluate this, remember the first problem that we've got is we have to decide what actual parameter values we're going to evaluate, at which we're going to evaluate the posterior. Because Bayes' rule doesn't give us a formula for this in complex problems. We have to sample it. And for this, we'll use a class of algorithms called variational methods, and they operate in a slightly different way than we've been using traditionally for some decades. Often what we do is no, okay, let me rephrase. So you can see this banana structure here, and let's say that is the posterior distribution, but that's the image of it that we can never see in high dimensional spaces. So we need to find samples that are distributed according to that structure. And then if we can get those samples, so that's going to be a set of parameter values. It turns out that we can simply estimate that integral by averaging over all of those different sets of parameter values. So this is going to be a way to estimate the integral I had on the previous page. So the way that these algorithms work now, it's a new class of algorithms coming out of machine learning and mathematical literature about 5-6 years ago. We start with our prior samples distributed according to our prior information, which might just be Gaussian in this case. And then the algorithms simply work by moving the models, the parameter values around until they self-distribute according to this structure. And this is nice because it means that in the end, we're going to get a set of parameter vectors which are distributed according to the posterior distribution, and at which we can now evaluate the integrals we can use to evaluate the integrals that give us the optimal answer. Okay, so let's have a look at the answer then. So we've now got, in this case, I think it was about 600, maybe 800 different vectors which describe the model. So we've got about 600 or 800 different images. This is the mean of those images, the average image. And at each point, this is the standard deviation, so the uncertainty across all those images. And this is our little reservoir. And we want to know what's the size of it. Well, let's zoom in on it. Here's the reservoir. And in the end, we want to know, what is the size of this. That's actually not that easy to define. So what is the size of this, that dark blue area? Is the size of the reservoir that darkish blue area or the bit that's blue at all? Those answers differ by more than a factor of 5 and completely change the decision that you make, probably, in reality. So we have a real problem here, particularly because actually the individual parameter vectors, the individual images look like this, because waveform data don't constrain models to be smooth at all. So all of the models that you get out, subsurface models here, are going to be speckly. And we have to use 600 of these to estimate the volume of the reservoir. So we need to now define our target function, which transforms any of these images into an estimate of the corresponding estimate of the volume. So one way to do this, I mean, the key thing here is that we need to define some threshold in seismic velocity in this case, which defines our boundary. Where are we going to say something's inside and something's outside? At which threshold? So we're going to have to answer a sub-question and really give some more inputs into this problem. And this is the difference between just solving an inverse problem where you can pretend you're being nice and objective and actually making a decision. Then you have to put in more information. We shouldn't be scared of that. So what we do is try to take a data-driven approach to deciding what thresholds to use. And this is an approach that you can use in many different kinds of problems. So let's just take a transect of cells here. Now we've got 600 models, let's say, and so we can take a histogram of the speed throughout all the models in each of those cells. So this is all of those, 7 cells. This is the histogram of the speeds. And what you can see if you just take those 2 central cells, which are these ones, you can see that the histogram is strongly biased towards low velocities. So we can be pretty sure that those 2 cells are inside the reservoir, not outside. Okay? If we look at the 2 outside cells, they show no evidence of bias towards low velocities. I mean, within the scatter of the histogram, there's no evidence. So to take a conservative approach, we'll call them outside of the reservoir because we don't want to overly expand the reservoir. So this is taking a conservative view of this. Now what we can do, because we can go through all or a few cells here and just work out which ones do we think are definitely inside, there's strong evidence that they're inside, and which ones are there's strong evidence that, there's 0 evidence that they're inside. And just take a few of those, and there's 10 outside and 6 inside here. And using all of the data from those, we can now construct 2 distribution functions called cumulative distributions. And just to understand this space is velocity, but it's actually seismic velocity threshold. So this is the thing that we want to define. We want to define the threshold which says what's inside and what's out. And there are 2 of them. This blue one is the probability that at a certain threshold, we will correctly define the inside cells to be inside. So essentially, if I put my threshold at 2, I will have about a 0.91 probability that I will correctly define these cells, the inside cells, as being inside. The other one works in the other direction and says, okay, what is if I define my threshold at, let's say, 2.5, In that case, I will only have a 0.3 probability of correctly defining the outside cells as outside. In fact, 70% of the time I will incorrectly assume that they are inside. So the reservoir will be too large. Now, just looking at these two graphs, there's only one point here which is unbiased. There's only one threshold you can choose, which will give an equal probability of assigning the inside cells as inside and the outside cells as outside. And it's this one here, so 1.7 or 1.8. So now we've gone through this process just to show you that you have to put some extra information in somehow, which is something about the question that you're answering, but in an unbiased way. So now we've got it solved. We've got the set of model vectors, if you like, the images that we've got 600 of those. We've got a target function which basically says, is any of those cells above or below 1.8 kilometers per second? And so now we can take any particular model and transform it into a reservoir volume, and we simply average this formula over all those different parameters. And here's an example. This is one of the actual images, and we just see that these are the cells which are defined as inside because they're above 1.8. And so that gives us a volume. If we then take the answer or histogrammed over all of the different vectors we see, or all of the different images, this is the true answer for the volume, and this red curve is the one that we get from the optimal answer. And this is the mean and the median answers. But note, the mean and the median you can't get without going through the same probabilistic analysis, because you still need to get the threshold. You have to find a threshold which is going to fairly define your reservoir and what's outside it. So you have to do something probabilistic to get that from the data. Now, the other thing about this is it's still quite blurred. We've still got an answer which is, it's quite broad in the range here, which may concern us. So we could, of course, just increase the frequency of the data. And if we increase it, for example, to 10 hertz, now the image tightens up, the threshold changes, but now you can see that by using the optimal answer, you're much, much less biased than using the others, the other forms like the mean or the median or anything else. So this is going through an analysis like this. I just decided to go through it to show you what's involved in trying to get an unbiased answer, or as unbiased as we can get it from the images that we might create. So now there are other ways to do this. Here is a slightly different model, and here are all the different models from another. This is just a 2D slice of a model, and you can see, as I say, they're all speckly. Now, what we could do is we could take each of those models and use them to create a migrated image, and here are all the migrated images. And now you can see the uncertainty in the structure directly in a migrated image. And so we could take a different approach where we actually start to interpret these movies directly. So here's an interpreter interpreting a movie manually, just picking the interfaces given the uncertainties in the subsurface. And of course, if we did this for all of our different interfaces, we wouldn't do it by hand, then we'd do it with a neural network or something, get it to pick these interfaces. Then we could define reservoir volumes or whatever we like. So there are different approaches to construct a target function, and this is a different one. But we still need to define the target function. We need to have parameters in order to find the optimal answer. So we need to do this in 3D, because we've got real CO2 storage problems coming up, real geothermal problems that we want to tackle, et cetera, et cetera. And in fact, those movies were in 3D. They were 2D slices from a 3D test model. So we can set this all up in 3D for small problems, small waveform inversion problems. It is roughly computationally feasible to get some sort of answer out that's reasonable. We can only do it for small problems, but what's okay about that, at least, is that energy transition problems are going to be smaller. You heard from Stuart yesterday, we are going to have far fewer data than we would have had in, say, oil and gas scenarios, because there's less money in it. This is a waste storage issue for CCS, currently at least. So in fact, the data sets will be smaller. We will be able to compute them. Compared to the cost of acquisition, the cost of all this processing is still roughly small, although the CO2 cost actually is increasing of the computation itself, but it's still way smaller than, it's not going to affect your overall budget of storing the CO2, whether you do or don't. Now, finally, what we've been looking at are questions like this. What is the volume of a particular reservoir? Has more than a kiloton of CO2 escaped from the subsurface store? What model best explains the seismicity? Those kind of questions. And all of these can be answered using a similar approach. Essentially, you can go through a similar process to compute answers to this kind of question. But actually, there are many real-world questions that are really quite different from this. And we still have to answer them. And in a moment, or right now actually, we're going to start looking at a different class of problems. And for this, I have a class participation exercise. So I'm going to give you all an exercise in a moment, and it's going to be really, really difficult. So I'm going to ask you to make a decision about something which I'm pretty sure nobody in this room has really very much prior knowledge at all. It's going to be well outside of your area of expertise, and that's fine. That's exactly as it should be. It's deliberate. But you have to make a decision. And I'm going to give you a decision to make, and I'm going to give you some evidence either way. Every single one of you must make a decision. Now, I'm never going to ask you for that decision. So you're never going to have to reveal it, so you're all safe. No one's ever going to know whether you were right or wrong. But you just have to make a decision, and you have to stick to it. Okay? You have to agree to this. Everybody has to do this. Okay. So the problem is this. This is the Siberian craton in the Lower Cambrian. And you can see it's a large landmass, but actually it's not a landmass, it's all below sea. Okay? And these different colors here are simply different facies from different water depths. And this is the Lower Cambrian, so up to about 514 million years. And this is after that period. And the difference that you can see between these two is that this purple color has come in, and these are now anoxic sediments. So this is what Rachel was talking about, the anoxia that she talked about. This is an example of large-scale anoxia. And what I'm going to ask you, I'm going to show you evidence for two different explanations for how this huge area became anoxic. In other words, how the seawater became anoxic, which was recorded in the sediments. And you have to decide which of the theory is the right one. Okay? Now, everyone must do this. You've got to make a decision. So take it seriously. Okay, I'm going to play you a narrative. Ooh, I hope this works. I didn't actually test the sound. It did work the other day, didn't it? Okay, right. So that's a shame, because we were going to collect some data that would have perhaps demonstrated what I was just going to show you in the last few slides. So other questions that one might ask in the real world, if one is a government or a company that has licenses for CO2 stores, is should we buy a license? So we know something about the subsurface. Should we go out and actually buy a license to store CO2? Or if I'm a CEO of a business, should this business enter the new sector, for example, of storing hydrogen or CO2 in the subsurface? Should we change our business model and now work in this different sector from what we've been working in before? And that's a key one, by the way, because we really want all of the hydrocarbon companies to make that decision. I mean, actually, most of them, or a lot of them, have already made that decision, at least in part, but we want all of them to start switching over. So important questions, which are still low dimensional or zero dimensional, but these questions now don't lie inside the model world. We don't have a model for them. They don't lie in our geophysical models, and the reason is that they depend on these other questions. Will there be a hydrogen storage market in 10, 20 years' time? What will the future interest, tax, discount rates, and so on be over the next 10 years? How rapidly will society's reliance on hydrocarbons abate over time? And what will our most experienced staff, who I need to convert to CO2 storage or hydrogen storage, what will they think? Will voters be inspired if I'm a politician? And how will my decision change the world itself? So if I start a company that will store hydrogen, that will affect people immediately around me. But if the CEO of Exxon starts to announce that they have shifted to hydrocarbon, that will change the entire world in one way or another. It changes the entire landscape in which I make these decisions. So now we enter this domain, which is where we have to escape from the model world into the real world to make the decision. We're no longer able to just compute it in the way that we did previously. So that previous machinery now doesn't apply. And we can still imagine Bayes' rule here. So for example, my investment decision will depend on the public spending and saving ratios, and perhaps these typically go up with wealth, but actually I get some data and it does the same thing. It actually constrains us in the other direction. So Bayes' rule would perhaps tell me, okay, actually, I don't expect people to be saving enough. So what I will do is I will, hang on, which way around? Saving enough, so I will reduce my credit card rates. Now, there's a bizarre, it doesn't matter. There's a bizarre inverted thing here that actually when you reduce credit card rates, interest rates, people spend less, not more, because they don't go into debt. And when people go into debt, they just stop caring and they just spend more. So if I raise interest rates, typically in a savings account, you expect people to save more, actually they spend more. So it's bizarre with credit cards. But you know, if in the real world, if I'm making decisions because I want to change the way people spend and save, then I might do different things than you might expect. But also our decisions depend on a huge number of dimensions. The population in 2045, the number of nuclear accidents that's happened between now and then, because nuclear is an alternative low carbon energy source. What is the climate militancy? Has that abated or increased in 2045? But of course, at every point in there, we might have an estimate of where we would sit in there, but at that point, we have another three axes. What will the income distribution be? And in every point in that space, we have another one. What will the temperature, the rainfall, what extremes will we have experienced? In that space, we've got insulation. How much will that have been applied to houses? Our industrial use, will there be lots of e-cars and et cetera, et cetera, et cetera? There are too many dimensions. And so we end up with this curse of dimensionality where we can't explore the space. We still have to make decisions about, you know, what is the actual amount of nuclear energy that we're going to prepare for now for 2045, because that's the scale up of time that we need. So we have to make decisions even though we can't explore the space anymore. And then we have another class of problems, which is Bayes' rules needs probabilities. I mean, here's our similar kind of thing to the spending and savings ratios, but now in 2030. Well, how am I ever going to get probabilities for these? Because I can ask a consultant like McKinsey to give me an estimate and they'll give me one, but then I can go to another consultant and they'll give me another one. And neither of them know the probabilities. So where am I going to get them? And in the end, government bonds will be set at some reason, some decision will be made, and that changes all my discount values. So that completely changes the decision. So the difficulty is that A, we can't explore the space, and B, we don't even have probabilities. There's no such thing as a probability value accessible. Yet, people are still making decisions. So what's happening between there and there? And there is a new analysis that's come out in the last 5 years, embodied in a theory called conviction narrative theory. And I just think, given our discussion over the last few days, this is quite important to understand. So this is summarized in a paper from Johnson et al. And this is a group of psychologists, decision theorists, management scientists, psychoanalysts. And they've been studying politicians, governors of the banks of the different countries in Europe, investment bankers, CEOs, so top-level people who have to make decisions under extreme uncertainty in cases where there are no probabilities. And this is the definition, this area where we have no probabilities, that is what is called radical uncertainty. So it's not just uncertainty that can be quantified, this is radical uncertainty where there is no quantification. So what do? It turns out, as you might have expected, they don't explore the space. They don't make optimal decisions, as we know. Under radical uncertainty, they explore very, very few options, and even one option out of that unexplorably large space where the curse of dimensionality was hitting us. And they make decisions based not on the facts that we give them, but on narratives. So this is what people are doing, not what we would like them to do. They make decisions based on narratives. So what's a narrative? A narrative is essentially a story. It's a fragment of a causal sort of sequence of events that makes sense, has some appeal. It's a story, or a part of a story. So mental representations that have causal, temporal, analogical, or valence, so good or bad information, in short, we'll just call them stories. So how they make decisions is that they select a narrative that explains the past and the present data. So essentially, they're using prior information. They've got the past and the present data, and they select a narrative that explains that sequence of data. And then they imagine it. They use that narrative and play it forward into the future. In other words, they forward model, but they do it in their heads. Okay, so this is a story, and they continue the story into the future. So there's their forward model, but now they need some data to evaluate it against. You know, in Bayes' rule, the likelihood, that's what it did. They're kind of operating a bit like Bayes' rule here. Now, they don't have any future data, so what they do is they evaluate that forward narrative based on how it affects them, with an A, not effect. So affect means how is it emotionally appealing to them. So this isn't now about is it consistent with facts or not, but actually, do they like it? Is it positive in some way? Are there aspects of it that appeal to them and they think it will appeal to others? And then they choose the narrative that they think will be appealing enough that it will create conviction for the correct people to take sustained action. Because unless you take a decision that will actually convince people to take sustained action, it's pointless. So these are the steps, and really it's very like what we do in Bayes' rule. It's just that the forward simulation is the brain. We play the narratives forward. We evaluate them against something. In this case, it's against our emotional response to that. And then they choose the one which is most appealing. Now, this is completely different to what we've heard about for decades from almost everyone who's been following the work from Kahneman, Tversky, these Nobel Prize-winning psychologists, economists. And essentially, their pretext for all their work is that rational thought is evidence-based, and emotions cloud the judgment of rational thought, of rational decisions. In fact, what is utterly revolutionary about this is now the psychologists are saying that this is not irrational, even though they're using emotion to judge. And the reason is that the new theory is saying that the emotional responses that we have to narratives are in fact learnt evaluations, rational, what we would have called rational evaluations, to long-term experience. So when I'm a kid, if I do something right, my parents say, oh, well done, ruffles your hair, gives you a wee cuddle, you know, and you have a pleasurable reward in some way for a rationally correct decision as judged by your parents. And that carries on through life. There are lots of examples throughout life where that happens. And so in a way, your emotional reaction to something is, in some sense, an approximate store of all your rational experiences. Now, that's the opposite of what Kahneman-Tversky said. It's the opposite. Now, of course, it's not always right. I like taking drugs, so it makes me feel good. So I take more drugs, and I feel better more of the time. But in the end, I take too many drugs, and I end up in hospital. So it doesn't always work, right? There are some ways in which, you know, our emotional responses are not good stores, but nevertheless, there's a building of evidence that actually this is consistent. So now finally then, just to say what are the matters arising from this, because this affects how we interact with people who are decision makers or within our science. So it describes what the decision makers do, not necessarily what we think they should do. Okay? But we are not trained decision makers, and they are. Remember, I mean, politicians are trained to make decisions. It's a very different way to view rationality from the traditional way. And what we see is that, I mean, what people do as a result of this methodology, if you like, is it might be rational in some cases, but how often? And we don't know that. That's not known yet. It's too recent, this theory. But then what else could they do? I mean, it's all very well to be critical of this, but what else are they going to do? What else could they compare their narratives to? There is no data. So maybe this is rational. Now, the test that we would have done, or the exercise we would have done, we would have collected some data that would have evaluated, in a way, your ability, or our ability, if you like, to make decisions under completely radical uncertainty. None of you would have had probabilities for that carbonate platform example. And it would have been well outside of your domain, just like every politician who gets parachuted into a job for 3 years. And if this is how, I think this is the key question. If this is how they do make decisions, well, now there's a theory for it. So what should we do in response? How should we present information to politicians? How should we interact with them if we think we know at least what answers they should not reach? I mean, we're not decision makers. We can't tell them exactly what to do. But maybe some things are just wrong. How are we going to convince them of that? And we saw examples. Stuart said of the CO2 storage in the UK, where 3 times now we've gone through competitions for a new store, and we still haven't got a store. 20 years, and the cost has gone up by a factor of 10, from 2 billion to 20. So what should we do? It seems to me that if we want to do anything, one thing we could do is to start thinking about that. How do we interact with politicians? We need some new models of this boundary between the model domain and the real world in order to help us make decisions. I'll stop there. Thanks.